Questions about anything? Well, today I'm going to say a few things about harmonic functions that I've been saving for you. I kind of hinted at some of these facts I'm going to talk about today. To get rolling, there's a very useful fact that if you have a harmonic function, so u is a real valued C2 smooth function that satisfies Laplacian u equals 0, so it's a harmonic function on a domain omega, well, then you automatically get an analytic function out of that, given by the real part of the analytic function f is du dx, and the imaginary part is minus du dy. Then it's a pretty easy consequence of the Cauchy-Riemann equations. Let's see. Du dx and du dy are, because u is C2 smooth, these are C1 smooth. Remember the Cauchy-Riemann equations, if you're going to use them to see that something's analytic, you need to know the real and imaginary parts are C1 smooth. So here the real part of my function f is let's call this thing a capital U. And let's let the capital V function be equal to minus du dy. Okay, so if then du dx and du dy are C1 smooth, and I need to check the Cauchy-Riemann equations. So let's check the Cauchy-Riemann equations now that we've got it set up so we can. Let's see, so there's my capital U. The question is du dx, let's see, capital U is little du dx, so that would be little u dx dx. And the big question is that equal to dv dy? And v is minus du dy. So that would be equal to minus du dy dy. And the answer is yes, because the Laplacian of u is equal to 0. And now the other one is du dy. Let's see, that would be du dy dx. And the question is that equal to minus dv dx? And minus dv dx, let's see, dv is minus du dy. V, capital V is minus d little u dy. And so this would be, minus and minus would be plus, and that would be du dy dx. I'm sorry, dx, first dx dy. In other words, you change the order. And that's a yes, because u is C2. C2 smooth. So that's all there is to it, yeah.
Why is it negative dv dx? Oh, never mind.
That's the Cauchy-Riemann equations.
It's not negative. I thought it was negative dv dy, but it's not.
No, that's the second, yeah, this is the second Cauchy-Riemann equation. And it's about capital U and capital V. So yeah, that's a routine thing to check. And here's a great application of it, a great consequence. I told you about this, and I never gave you a convincing demonstration of it. But if U is a C2 smooth, real-valued harmonic function, on a domain, let's see, it's got to be a simply connected domain. On a simply connected domain, which means a domain with no holes. Then U has a harmonic conjugate. I would call it a global harmonic conjugate. We saw that there's problems that arise if there's holes. If there's no holes, then there's no problems. So then U has a harmonic conjugate. On omega. I call that a global one. It's one that works on the whole of omega. You can always do it locally on a disk. The big question is, can you piece those together and get one on the whole region? The answer is yes. And we won't have to use topology to do this because we have some facts at our disposal here. So I'm going to think out loud here for a second. If F is equal to U plus IV is analytic. So if I had a harmonic conjugate, I would have F equals U plus IV if it's analytic. Then we had red box number 1 and red box number 2. Remember what they were? Their F prime could be either du dx plus I dv dx. That was red box number 1 that I got by differentiating in the horizontal direction. And then red box number 2 I got by differentiating in the vertical direction. And that one was dv dy minus I du dy. And we got the Cauchy-Riemann equations by equating red box number 1 and red box number 2. But now when you look at those, you realize, oh, that's equal to, let's see, I'll leave the real part I like, du dx. But I can change the dv dx into a derivative with respect to u. So if I'm just using the Cauchy-Riemann equations here. Du dx is, I'm going to leave, but dv dx I'm going to replace by minus I du dy. So I'm using the top line to get the real part and the bottom line to get the imaginary part. And that's the thing I just talked about above. When you have a harmonic function, we know that that's analytic, independent of knowing if there's a v or not. So the aha is, we know this is analytic. And if we had a harmonic conjugate, then we'd have this f prime. And those two things would be the same. That's the exciting thing. So the idea is if I want to get a harmonic conjugate, I should find an antiderivative of that red thing. So I'm thinking out loud here. Now I'm going to do it. That's where I get my big idea. Big idea is, let's let capital F be equal to du dx minus du dy. We know that on a simply connected domain, analytic functions have analytic antiderivatives, since that followed from the Cauchy theorem. Omega is simply connected. We know there's an analytic antiderivative for this capital F. And hopefully that's going to give me the harmonic conjugate I want. I have to think about that. So we know there is an F. So I didn't define that F above. I was just thinking out loud. Maybe I should call it a G, but I think I'll call it an F anyway. There is an analytic function f such that f prime equals capital F on omega with little f prime equals capital F. In fact, we knew how to construct it. In fact, I can define the f of z to be an integral along any old curve that starts at a fixed point A and goes to z and is f of w dw. I guess that's just a remark. I don't have to care about that. Let's write f equals capital U plus IV. Now I'm going to do that red box number 1 and red box number 2 thing. We know that f prime is equal to capital du dx plus I capital dv dx. And it's also equal to dv dy minus I du dy. It's red box number 1 and number 2. And now we know that that's equal to the capital F thing. That's little du dx minus I du dy. When you equate those two, let's see, I'm going to equate some real and imaginary parts here. If I look at this real part here, that's equal to the du dx. So I see that d little u dx is the same as d capital U dx. That's nice to know. Then when I look at this spot here, pick a different color. How about green? Look in this spot. The imaginary parts there are equal. I see that the derivative with respect to y's are the same. So the aha here is the gradient of capital U is equal to the gradient of little u on omega. So they differ by a constant. That's true on any connected domain. If their gradients are the same, they differ by a constant. So let's write little u equals capital U plus C. I claim now that capital V is a harmonic conjugate. I guess that's obvious. For little u. Let's see, why would that be the case? Y. U plus IV is equal to, let's see, little u, that would be capital U plus C plus IV. And that's equal to, let's see, capital U plus IV was my my little f plus C. And so sure enough, that's analytic. That's all there is to that. Questions about that? So that's nice to know. And by the way, if I wrote this, Mike, that integral formula I had for my little f, that capital F was equal to du dx minus I du dy. And if I wrote that in and made it into real integrals, this would be exactly the same integral you'd use to find a potential function in physics. It turns out to be exactly the same thing, just different way of looking at it. If you looked at your physics formulas for the potential function, you'd see things that look familiar when you did that. Were there questions? That's kind of a fun thing to do, because then you'll start seeing things that look familiar. Okay, since I'm sort of putting up loose ends together about harmonic functions, I should mention there's a Liouville's theorem for harmonic functions. So let's suppose U is harmonic on the whole complex plane. On C, and bounded there. Then it's constant. So there's no fancy word for entire harmonic functions. They're just harmonic on the whole complex plane. Then the conclusion is then U must be constant. And the proof's a one-liner. Let's get a harmonic conjugate. I did this calculation using calculus on the whole complex plane, but I could use my theorem I just showed you. The whole complex plane doesn't have any holes, so I can get a harmonic conjugate. V for U on the whole complex plane. Then F equals U plus IV is entire. And I told you that important trick last time. The trick is if I think of the exponential function, I can write e to the f, that would be e to the u plus IV. That's e to the u times e to the IV. And when I take the modulus of that, e to the f modulus would be the modulus of e to the u, which is a real positive number. So, of course, the modulus of that is itself. This one has modulus 1, because that's an e to the I theta for some angle, except theta is v there. And of course, this one being a real positive number, this would be e to the u. And so the modulus is equal to e to the u. And if e to the u, let's say we have a u is less than, this is interesting, I'm only having u bounded from above. So let's say u is less than or equal to m, then this would be less than or equal to e to the m, because the exponential is a strictly increasing function. And of course, e to the f is an entire function. And so now it's a bounded entire function. E to the f is bounded entire. So Liouville's implies it's constant. The Liouville's for analytic functions. This would be a complex constant, perhaps. And now you ask yourself, if u is constant, And the answer, of course, is yes, because, let's see why. The easiest way to see it is that above there we have, so I claim u is constant too. I have to think about it, though. Let's see, I have e to the u is the modulus of e to the f, and e to the f is constant, so e to the u would be constant modulus of c. And this is a real value. U is real, and of course it's the real exponential. And so this means that u is the natural log of the modulus of c. So check. That's a constant. So I should have said, to make this a fancier theorem, if a harmonic function is bounded from above, then it's constant. Maybe that's worth a remark. The proof shows if u is bounded above, then u is constant. And the same would hold if it's bounded below. Apply to minus u in place of u. See, if it's bounded below, then it's constant. Cu bounded below implies that u is constant, too. So any questions about that? That's an easy one. I want to think about a question now. It's natural to ask. We were able to deduce all those fancy things about analytic functions from Cauchy integral formula. And you might ask, well, this is kind of feeling like harmonic functions act a lot like analytic functions. The question, is there a Cauchy integral formula for harmonic functions? I'll put it in quotes because it's not called this, a Cauchy integral formula. For harmonic functions. Well, the answer is going to be yes, and it's called the Poisson integral formula, famous thing. Poisson is in my family tree. Yeah, about 10 generations back. In fact, I'm obsessed with this question, kind of, so I've been thinking about it for a long time. And when I got all my ideas sorted out, I wrote a short paper about it, expository paper, which I put on the home page. On the home page, called Something About Poisson and Dirichlet. Anyway, I deduced the Poisson formula from scratch there in sort of the shortest way possible. Maybe there is a shorter way, but it's the shortest way I've ever found. So, something about Poisson and Dirichlet. The Poisson integral formula solves the Dirichlet problem. And they were sort of contemporaneous students of Fourier. Okay, so let me show you how to cook this thing up. Let's suppose this is from the book, and it's very short and sweet. The thing that's not satisfying about it is they kind of pull something out of the thin air to make it work. And you can figure that out without pulling it out of thin air. It just takes more time to talk about. That's why I'm going to skip it. So let's suppose U is harmonic. I'm going to make a slightly bigger disk than the unit disk. So it's going to be harmonic on the disk of radius r about 0, where r is slightly bigger than 1. Could be a lot bigger than 1, but it's at least a little bit bigger than 1. Then we know we can get a harmonic conjugate. So we get an analytic F equals U plus IV. This analytic on this bigger disk. And let's let A be a point inside the unit disk. And let's let C10 be the unit circle. So that'd be parametrized by 0 plus 1 times e to the it, as t goes from 0 to 2 pi. Okay, we know the Cauchy integral formula. So naturally, when I got the averaging property for harmonic functions, all I did was take the real part of the Cauchy integral formula. Let's see. I'll put 1 over z minus a out in front and put my f of z here and my dz here. That's just the Cauchy integral formula. At the center, if a was 0, then I could write that out, and I'd get a very simple way to take the real and imaginary parts. We want to take the real part, so we get a formula for the u of a. But it's a mess. So you get a formula for u of a. But it's a mess, and in fact, if I wrote it all out in terms of u's and v's, it'd be a jumbled up mess in terms of both u and v. It's a mess. Involving both u and v, which is kind of a bummer. And so it's not a pretty formula to look at. But here's the trick. The trick is, let's see, if I calculate integral of a conjugate 1 minus a conjugate z, f of z dz. This is what I'm pulling out of thin air. That is a big fat 0, because if you set that denominator equal to 0, let's calculate here. 1 minus a bar z equals 0. Then you'd get that z is equal to 1 over a bar. And the modulus of a is less than 1. And the modulus of a bar is equal to the modulus of a. And so the modulus of 1 over a bar is bigger than 1. So that the bad spot there is outside the unit disk. The pole, that would have a pole, and it's outside the unit disk. So this thing right here is analytic inside and on. inside and on the unit circle. So Cauchy's theorem means it's a big fat zero. So that is a big fat zero. And it's a big fat zero even if I put a 1 over 2 pi and I in front of it. Okay, so that's the trick I'm going to do. And now the miracle, which is too good to believe. God, suddenly don't remember how to spell miracle. Okay, f of a, I'm going to write out the Cauchy integral formula. I'm going to put some stuff in here. I'm going to put the f of z here, dz. Cauchy integral formula is 1 over z minus a. That spits out f of a. And then I'm going to subtract this thing that gives me the zero stuff. Minus a bar over 1 minus a bar z. That adds a 0. I'm adding a 0 here. Or actually, I'm subtracting a 0. And a miracle happens when I do some algebra. Let's see. I'm going to write this out. Let's do it. Oops, we're my 1 over 2 pi I. Sorry. That's going to be 1 over 2 pi I, integral from 0 to 2 pi, 1 over e to the it minus a bar over 1 minus a bar e to the it, f of e to the it, dz is I e to the it dt. These two things on the bottom are conjugates of each other. So when I multiply those together and do cross multiplication, those two things are that's going to give me the modulus of the denominator squared. Okay, let's see. And notice this I here cancels this I here. That's kind of nice. And when I do the cross multiplication, I get 1 over 2 pi integral from 0 to 2 pi. Okay, I told you those two things are conjugates. So the denominator is going to be I like the first one, e to the it minus a squared. Are those conjugates of each other?
Well, A is equal to
Yes, they are, because if let's see, what? E to the minus it times e to the it. I'm not going to say that. You just do it. Let's see, when I multiply. Are those the conjugates? I thought this was going to be obvious. E. Oh. Yeah, no. This is a true thing. If I make that e to the it and e to the minus it, oh gosh, I guess I have to do it. All right. I'm gonna write this thing as 1 over e to the minus it. Then when I do that, they're going to be conjugates. What? Okay, so I'm going to put the e to the it here. I like that. And then I have e to the it minus a. But when I distribute it through the other one, I'll use this version of it. And when I do that, I'll get minus a bar over e to the minus it minus a bar. Where'd my z go? Oh, my z is e to the it. Oh, that's 1. Okay, hallelujah. So now I see that, yeah, these things are now conjugates. Anyway, it's just algebra. I should have said that in the beginning and skipped all this. Conjugates. And I get a dt. And now finally, when I do it all, when I do the cross multiplication, oh yeah, that better be there, yeah, f of e to the it. The miracle's about to happen. The miracle is that now I get a 1 over 2 pi, and when I do the cross multiplication, in the denominator is the modulus of e to the it minus a squared, because those two things are conjugates now. And the top, you do a miracle happens and some stuff cancels, and on the top is 1 minus the modulus of a squared. And here you get, so the miracle is this thing is real valued. And so now when I take the real part, since that's a real valued thing, I can take the real part now. And I get the famous Poisson formula. U of a equals 1 over 2 pi integral from 0 to 2 pi 1 minus the modulus of a squared over e to the it minus a squared. And notice when I take the real part of that integral, f is a u plus iv. So I'd get the u1 plus I times the v1. And so when I take real parts, what goes here is u of e to the it. So that's kind of a mind-blowing thing. It means that harmonic functions are like analytic functions. If you know them on the outer circle, on the outer curve, they're completely determined inside. Okay, that's a biggie. That's the Poisson integral formula for the unit circle, disk. That's my favorite form of it because it involves pretty geometric things. Let's see, what's the geometry here? I've got my circle of radius 1. There's the origin. Let me write, here's A. A, let's let A be equal to R e to the I theta. And here's an e to the it. And of course, this is the unit disk. So, let me use some colors here. I'll make this distance blue and this distance green. And this distance from the 0 to e to the it, that's 1, because it's radius 1. This blue distance would be r, because writing a as r e to the I theta. And so if I use the, let's see, I've got angles here. I've got this angle. Let me put a little horizontal here. This angle is theta. And this angle is t. And so that angle in the triangle is theta minus t. And so if I were to do the law of cosines, let's do the law of cosines. Let's see. D squared. Let's see. What's the law of triangle? If that thing were a right angle, then the law of cosines would say d squared equals 1 squared plus r squared minus 2r times 1 cosine theta minus t. If that angle theta minus t was a right angle, that would be a right triangle, and this would be Pythagorean theorem. So the law of cosines is like a correction term if it's not a right angle. That's the way I remember law of cosines. Okay. And that's exactly, that distance in the bottom, d, green d, is the denominator in Poisson's formula. And of course, the modulus of A is little r. And so the real version of the Poisson formula is u of r e to the I theta is equal to 1 over 2 pi integral from 0 to 2 pi. Famous formula, 1 minus r squared over 1 plus r squared minus 2r cosine theta minus t. And here we put u of e to the it dt. You can deduce this famous real formula by using real Fourier series and separation of variables. That's the way I do it in Math 428, my other class that I'm teaching. So I get confused about what I might have taught. Feels awfully familiar. You can also do this on a circle. I could do this on any old circle. Do it on a circle of radius. Let me do it on capital R, circle of radius capital R about not the origin, but about z naught. Then you get the formula u at z naught plus r e to the I theta is equal to 1 over 2 pi. Very similar looking formula, except in place of 1, you have capital R. So you have r squared minus little r squared. And you have capital R squared plus little r squared minus 2rr cosine theta minus t. And now on the boundary, you'd have u of z naught plus r e to the it. Here's an exciting fact. So if I have a harmonic function, this is a true thing. But you look at that formula. So the Dirichlet problem the other name and the famous name from that period. The Dirichlet problem is given a continuous function, I'll do it on the unit disk, a continuous real-valued function, phi on 0, 2 pi that hooks up. So it's actually continuous on the circle. The problem is find a function u that's continuous on the closed unit disk. So that's going to be continuous up to the closed circle. So it's got to be continuous on there, harmonic on the inside. With the proper boundary values, with u of e to the I theta equal phi of theta. An exciting fact, you look at those Poisson formulas. If I had such a thing, they would be given by those Poisson formulas. And the exciting thing is that those formulas solve the problem. So an exciting fact. The Poisson formula solves the problem. Solves the Dirichlet problem. So the answer is going to be u of r e to the I theta is going to be 1 over 2 pi. Let's see. Instead of writing the whole thing out, it's traditional to write out that thing of r theta t. That's the Poisson kernel. And here we put f of t dt. And this is the Poisson kernel. Which is 1 over 2 pi, 1 minus r squared over e to the it minus r e to the I theta squared. Let's say I've got a t there. Oh, yeah, there's a t and a theta. That's exciting. The proof of that fact is called Schwarz's theorem. I guess Dirichlet didn't figure it out at the time. Poisson wrote a nice formula, and then it was up to Schwarz, who came later, to demonstrate that it all worked. Yeah.
F should be phi.
What?
Should that F be phi?
Oh, yeah. That's my Math 428 notation. This is phi. Thanks. Let's see. That's a good place to quit today. Any last minute question? Yeah.
What's the significance of the Dirichlet problem?
Oh, I should tell you, yeah. This is a heat problem. So harmonic functions satisfy Laplacian as 0. That's steady state heat. So I'm looking for the steady state solution heat with those boundary values. So if I know the temperature on the boundary,